There is a place where the sun does not rise like a distant lamp, but like a presence that fills the sky. On Mercury, sunlight can be more than 6 times as intense as it is on Earth. The ground receives that light without oceans to absorb it, without clouds to scatter it, and without a thick atmosphere to carry warmth from one region to another. Across the long Mercurian day, rock can become hot enough to melt lead in some places, while shadowed hollows near the poles remain cold enough to preserve water ice. This is not the hottest planet. Venus holds that distinction beneath its dense atmosphere. Mercury is something stranger, a world of sharp contrasts, where heat and cold sit close together because almost nothing stands between the surface and space. From a distance, Mercury can look simple. It is small, grey, and heavily cratered. Its surface resembles the moon, and for a long time that resemblance encouraged the idea that Mercury was little more than an old, inactive stone beside the sun. But the closer the planet has been examined, the less simple it has become. Its cliffs run for hundreds of miles, marking places where the crust was compressed as the interior cooled. Broad plains reveal that lava once spread across the surface. Great impact basins record collisions powerful enough to reshape entire regions. Bright hollows found inside craters and along exposed slopes suggest that the surface has changed on surprisingly recent geological timescales. Mercury also carries an unusually large metallic core. Beneath a crust, only a small fraction of the planet's radius. Iron-rich material extends through most of the interior. The planet is small, yet it is dense. It has cooled deeply, yet part of its core remains fluid enough to help sustain a magnetic field. That field is weak compared with Earth's, but it creates a small magnetosphere around the planet. The solar wind presses against it, bends it, and sometimes drives charged particles toward the surface. Mercury is not simply sitting beside the sun, it is continually interacting with it. The planet moves quickly through space, completing an orbit in only 88 Earth days, yet it turns so slowly that one sunrise to the next lasts 176 Earth days. The motion of the sun across the Mercurian sky would seem unfamiliar. In some locations, it would appear to pause, reverse direction for a time, and then continue, the result of Mercury's rotation combined with its changing orbital speed. All of these features belong to the same story. Mercury is a surviving record of the early solar system, a planet shaped by impacts, volcanic eruptions, internal cooling, gravitational strain, and relentless exposure to the nearby sun. Its surface holds traces of processes that began more than 4 billion years ago. But those traces are not arranged like pages in a book. They overlap. They have been broken, buried, heated, and exposed again. To understand Mercury, we have to move slowly across that damaged ground. We will begin with the planet's birth, when metal and rock were gathering near a young sun. Then we will follow the collisions that scarred its crust, the lava that filled its lowlands, the cooling interior that tightened the planet like a contracting shell, and the sunlight that continues to alter its surface today. Mercury does not tell its history in a single dramatic event. It tells it through craters, cliffs, plains, shadows, and the patient survival of stone. The story of Mercury begins before there was a planet to name. Around 4.5 billion years ago, the young sun was surrounded by a broad disk of gas and dust. Within that disk, grains collided, clung together, and gradually became larger bodies. Some material remained small, some gathered into rocky fragments, some fragments grew into planetesimals, and those planetesimals began to pull more matter toward themselves through gravity. Mercury formed in the innermost region of this changing disk, where high and orbital motion was rapid. The young sun was more active than it is today. Radiation, charged particles, and repeated collisions shaped the material nearby. Yet Mercury was not assembled from melted metal alone. Its surviving surface contains sulfur, potassium, sodium, and other elements that can be lost when rock is exposed to prolonged heating. That discovery changed the way scientists think about Mercury's beginning. For many years, its large metallic core seemed to suggest a simple explanation. Perhaps the early planet had once possessed a thicker outer layer of silicate rock, more like the proportions found inside Earth or Venus. Then a massive collision might have removed much of that mantle, leaving behind a world dominated by metal. Such an event is physically possible. The early solar system was filled with impacts, and some were large enough to alter entire planets. Earth's moon probably formed after a giant collision. Uranus may have been tipped by one Mercury. Moving through the crowded inner solar system would not have escaped that violent period. But the details remain difficult. A collision, energetic enough to strip away much of Mercury's rocky exterior, would also produce intense heat. Some models suggest that vaporized rock could later fall back onto the planet. Others indicate that much of the lost material might remain nearby rather than disappearing completely. And if the impact removed the outer layers so thoroughly, scientists must still explain why Mercury retained substances that are easily driven away by heat. Another family of ideas looks toward the young sun. Perhaps strong solar radiation heated the surface of a larger early Mercury until some rocky material evaporated. Perhaps an intense solar wind carried lighter material away before the planet fully settled into its present form. This picture gives the sun a direct role in creating Mercury's unusual proportions, yet it faces a similar problem. Mercury is not as depleted in volatile elements as such severe heating might predict. The planet formed close to the sun, but its chemistry does not resemble a simple residue left after everything easily vaporized had been removed. A third possibility begins even earlier, inside the disk itself. The material available near Mercury's orbit may already have been richer in metal than the material that gathered farther out. Tiny particles of iron and silicate do not always move through a disk in the same way. Magnetic forces, differences in condensation, and the sorting effects of gas could have concentrated metal in certain regions. In that case, Mercury may not have lost most of a rocky mantle. It may have been built from unusual ingredients from the beginning. There are variations within each of these ideas, and none has closed the question. Mercury may preserve the result of several processes rather than one. Its starting material could have been metal-rich. Later collisions could have changed its mass. Heat from impacts and radioactive decay could have separated the interior into layers. Solar radiation could have altered the surface without fully determining the planet's composition. The surviving world is the sum of all those changes. As Mercury grew, gravitational energy was converted into heat. Impacts added more. Radioactive elements within the rock released heat as they decayed. Metal, denser than silicate material, sank toward the center. Lighter rock rose above it. This separation, called differentiation, created the broad internal structure Mercury still carries, a metallic core surrounded by a comparatively thin rocky shell. The core occupies about 85% of the planet's radius. That number describes distance from the center, not total volume, but it reveals how little room remains for the mantle and crust. If Mercury were opened from pole to pole, most of the cross-section would be core. The planet's present density also carries the memory of that structure. Mercury is the second densest planet in the solar system after Earth. Earth's gravity compresses its interior more strongly because Earth is much larger. When that compressive effect is considered, Mercury's high proportion of metal becomes even more striking. But its core is not simply a solid sphere of iron. Evidence from Mercury's rotation, gravity, and magnetic field indicates a layered interior, with at least part of the core still liquid. Sulfur and perhaps other lighter elements can lower the melting temperature of metallic material, allowing liquid to persist inside a small planet that has been cooling for billions of years. Deeper within, a solid inner core may occupy a substantial part of the center. Above this metallic interior lies a mantle far thinner than Earth's, and above that, a crust assembled from old volcanic rock, impact debris, and material altered by exposure to space. There was a time when much of this outer shell was hot enough to move. The young planet held more internal heat than it does now. Magma could rise through fractures, spread across low ground, and cool into broad plains. Large impacts opened deep basins, changing pressure below the surface and creating pathways for molten rock. The planet visible today was still being built from below, even as it was being broken from above. Nothing from that era survives untouched. Every early surface was exposed to later impacts. Every basin changed the stresses around it. Every lava flow covered something older. The earliest record lies beneath younger plains, inside mixed fragments, and within chemical patterns measured from orbit. This is why Mercury's origin remains a scientific reconstruction rather than a single preserved scene. The planet offers consequences without showing every cause. Its oversized core is real. Its volatile elements are real. Its old volcanic crust is real. The challenge is finding one history, or a sequence of histories, that can account for all of them at once. Near the young sun, metal and stone gathered into a world whose first chapter has never been fully erased. It has only been buried beneath everything that happened next. The oldest landscapes on Mercury are crowded with circles. Some are broad and shallow, their rims worn down by later collisions. Others cut across older craters, leaving sharp walls and brighter rays of broken material. Between them lie chains of smaller pits, overlapping basins, and stretches of ground so heavily struck that almost every visible surface belongs to more than one event. This pattern formed during an era when the inner solar system still contained large amounts of wandering debris. Asteroids and smaller rocky bodies crossed the paths of the young planets. Their speeds were high, and Mercury's own rapid orbit around the Sun added to the energy of many encounters. An impact on Mercury does not need an atmosphere to announce its arrival. There is no thick layer of air to slow a projectile or break it apart before it reaches the ground. The incoming body meets the surface at cosmic speed, and its motion is converted almost instantly pressure, heat, fractured rock, and outward moving shock waves. For a brief interval, the target behaves less like solid stone and more like a material being forced aside. Rock is crushed, melted, and thrown outward. A cavity opens. Its walls collapse. In larger impacts, the floor rebounds upward before settling again, producing central peaks or rings of mountains. What remains is not a simple hole. A crater is a frozen sequence of motion. Its rim marks displaced ground. Its ejector blanket records material thrown beyond the cavity. Its interior may hold melted rock that cooled after the impact. Smaller pits around it may have been formed by fragments returning to the surface. Scientists read these relationships in much the same way that a reader follows layers of writing on an old page. A crater that lies across another crater must be younger. A lava plain that covers part of a rim must have arrived later. A fault that cuts through both belongs to a still later stage. There are no exposed sedimentary layers on Mercury that preserve fossils or seasons. Time is reconstructed through overlap erosion by later impacts and the changing density of craters across different terrains. The most heavily cratered ground is usually the oldest. Smother plains with fewer impacts are younger, at least in a relative sense. Bright rays around a fresh crater will fade as tiny impacts and charged particles alter the exposed material. Sharp edges become muted. Ejecta is mixed into the ground around it. This gradual alteration is known as space weathering. On Mercury, it takes place beneath intense sunlight and within the flow of particles from the sun. Microscopic impacts melt small patches of soil. Solar radiation changes exposed minerals. Over long periods, a freshly disturbed surface loses some of its contrast and begins to resemble the older terrain around it. Yet even among countless scars, one structure dominates Mercury's geological memory. The Caloris Basin stretches roughly 1,500 kilometers from one side to the other. It is so large the journey across it would cover a substantial fraction of Mercury's diameter. And from orbit, its boundary forms a broad ring of mountains and broken terrain surrounding an interior later filled and reshaped. Galactite, the object that made Caloris, struck billions of years ago during the heavy impact history of the inner solar system. Its exact size and approach cannot be reconstructed with certainty, but the energy released was sufficient to excavate deep crust, raise immense rings of rock, and send material across much of the planet. Shockwaves moved into the interior. Fractured rock traveled outward. Ejecta rose above the surface and fell across surrounding regions. Some fragments landed nearby. Others traveled far enough to produce secondary craters at great distances from the basin. Then came the longer response. The newly opened cavity adjusted under gravity. Its floor rose and settled. Faults formed. Melted material pooled in low areas. Beneath the damaged crust, pressure changed, creating pathways through which magma could later reach the surface. Caloris is therefore not the mark of one instant alone. It is a landscape built by impact and then revised by the planet beneath it. When Mariner 10 passed Mercury in the 1970s, the basin appeared near the edge of the illuminated hemisphere. The spacecraft could see only part of it, and the incomplete view left its full scale uncertain. More than 3 decades later, Messinger observed the basin from new angles and eventually from orbit, revealing its complete outline and the broad volcanic plains within it. One generation first saw a partial ring near the border of an image. Another received global maps in which Caloris could be placed among surrounding plains, faults, craters, and compositional differences. The same ancient impact waited through all that time, while instruments slowly gained the ability to see its wider setting. Inside the basin, the ground does not simply slope toward a central low point. Its interior contains ridges, fractures, younger craters, and extensive plains. Some parts have been raised rather than left as the deepest ground. Structure records how the crust responded after the impact and how later volcanic and tectonic processes continued to modify it. Near the center lies a crater named Apollodorus. Around it, long troughs radiate outward in a pattern, sometimes compared to the legs of a spider. The crater and the radiating fractures may not have formed in the same event, and their relationship remains under study. The fractures themselves show that the basin floor was pulled apart in places. Elsewhere, ridges reveal compression. This combination suggests that stresses changed over time as the interior plains cooled, the crust adjusted, and Mercury continued its broader contraction. Far from Caloris, on the opposite side of the planet, lies an area of disrupted hills and valleys known as the antipodal terrain. For years, scientists proposed that shockwaves from the Caloris impact traveled through Mercury and met on the far side, breaking the crust where their energy converged. That idea remains plausible, though later mapping has encouraged closer study of the terrain's timing and origin. Around the basin, great fields of ejecta preserve the outward force of the collision. Some terrain appears ridged and lineated, shaped by material moving away from Caloris. Secondary craters form chains and clusters where large fragments return to the surface. These secondary impacts matter because they complicate the use of crater numbers as a clock. Not every crater represents a separate asteroid, a arriving directly from space. One large collision can create many smaller craters, all at nearly the same time. Scientists therefore examine more than the total number of circles. They study shapes, clustering, rays, degradation, local geology, and the way craters interact with plains and faults. Across Mercury, other large basins preserve different stages of this impact history. Some are older than Caloris, and so worn that their original boundaries are difficult to trace. Others are younger and retain clearer rings, terraces, and fields of ejecta. The Rembrandt Basin, for example, is a large impact structure whose interior contains both volcanic plains and tectonic features. The Radit-Ladi Basin is younger, with a more sharply preserved rim and a floor crossed by troughs. Each basin becomes a local record of what Mercury was like when the impact occurred and how the planet changed afterward. A younger crater may expose dark material from beneath brighter plains. Another may reveal a patch of unusual composition. Some impacts dig only through loose surface debris. Larger ones reach deeper, bringing buried rock into view. In this way, impacts both erase and uncover. They destroy older landscapes, but they also excavate material that would otherwise remain hidden. They break the crust, yet the fractures they create can allow molten rock or volatile bearing material to move. They make the surface harder to read while providing some of the clearest windows into its depths. For the young Mercury, the bombardment was not a separate prelude before geological activity began. It was part of the activity itself. Large collisions changed the flow of heat through the crust. They produced melt. They created basins that later collected lava. They rearranged the stresses acting across entire regions. The distinction between impact history and volcanic history is useful, but on the surface the two are often interwoven. A basin opens. The ground adjusts. Magma finds a path upward. Lava spreads across the floor. New craters appear on the cooled plain. Faults later cut through them. That sequence may take hundreds of millions of years, yet from orbit it can occupy a single field of view. Caloris holds this kind of layered time on a planetary scale. Its ring marks a collision from the distant past. Its plains belong to eruptions that followed. Its ridges and troughs preserve changing stress. Its younger craters show that the surface remained exposed to the continuing traffic of the solar system. The impact did not finish the landscape. It prepared a place where the planet's internal heat could write over the scar. The lava that followed the great impacts did not build tall mountains. On Mercury, most volcanic rock spread outward. Instead, molten material rose through fractures in the crust, reached the surface, and moved across low ground in broad sheets. Some flows entered old craters and filled them almost to their rims. Others crossed earlier plains, buried smaller scars, and left only the upper arcs of crater walls visible above the new surface. From orbit, these partly drowned circles are among the clearest signs that the plains are volcanic. An impact could make a smooth pool of melted rock inside a crater, but it would not normally flood a wide region, pass around obstacles, and bury many unrelated craters beneath one continuous layer. Mercury's northern plains preserve this pattern on an immense scale. They cover a region comparable in area to a large part of a continent on Earth. Their surface is smoother and less densely cratered than the terrain around them, showing that the lava arrived after much of the older ground had already formed. The flows were probably low in viscosity, able to travel far before cooling. Instead of piling up near a single vent, they spread thinly across the landscape. Repeated eruptions could place one layer over another until deep basins became broad plains, and the older topography was softened beneath volcanic rock. This kind of volcanism leaves a planet without the familiar outlines of volcanoes. On Earth, many people first imagine a steep cone rising above the surrounding land. But a volcano is not defined by a mountain. It is any place where material from the interior reaches the surface. When lava is fluid and erupts rapidly, the result may be a plain so wide that its source is difficult to identify. Mercury contains few obvious volcanic edifices. There are no chains of towering cones like those along Earth's plate boundaries, and no single shield comparable to the largest volcanoes on Mars. The planet's volcanic history is written mainly in surfaces that look level from a distance. The lack of large cones may also reflect how the crust behaved. Mercury has no system of moving plates like Earth's. Its volcanic pathways were shaped by impacts, cooling stresses, and fractures that opened as the interior changed. Magma could rise through these temporary routes, spread across the ground, and then lose access when the fracture closed or the supply below diminished. A later eruption might begin somewhere else. This scattered pattern makes the original vents hard to find. Billions of years of impacts have also damaged the flow boundaries. Younger craters have broken the plains, and space weathering has reduced some of the color differences between neighboring units. Even so, the broad sequence remains visible. Much of Mercury's major lava flooding occurred early, while the interior still held enough heat to generate large volumes of melt. Some eruptions predated Caloris. Others followed the basin-forming impact and filled parts of its interior. Still others resurfaced regions far from the basin during later intervals. Inside Caloris, volcanic plains cover much of the floor. Their color and texture differ from parts of the surrounding terrain, and younger craters have punched through them to expose darker material below. The basin became both a scar and a container, a low region where lava could collect after the crust had been fractured by impact. The plains did not arrive all at once. Ridges and troughs cut some surfaces, but are covered by others, revealing alternating periods of eruption and deformation. One lava layer cooled, the crust shifted. Another flow crossed the changed ground. Later impacts added a new set of circles. Each surface was temporary, even when it remained exposed for millions of years. In the northern plains, broad rises and buried crater rims show that the lava was thick enough in places to transform the earlier landscape, yet the individual flows are often difficult to separate. Mercury's sunlight alters visible color, and the flows may have had similar compositions. Their boundaries can disappear into one another until a long history of separate eruptions looks like a single plane. The chemistry, measured by Messinger, also changed the old picture of a dry, depleted world. Mercury's surface contains more sulfur than many early models predicted. It also contains other elements that would have been difficult to retain if the planet had simply been baked until nearly every volatile substance escaped. These materials do not mean that Mercury was cool or wet. They mean its formation and volcanic chemistry were more complicated than distance from the Sun alone would suggest. Volatile substances dissolved in magma can change what happens when that magma approaches the surface. Deep underground, pressure helps keep gases within molten rock. As magma rises and pressure falls, those gases can separate and expand. If enough gas is present, an eruption can become explosive, breaking molten material into fragments and scattering it around a vent. Mercury preserves evidence that this happened. Across the planet, irregular pits appear within bright or reddish deposits that spread over the surrounding terrain. These pits do not have the raised rims expected from ordinary impact craters. Many sit inside older craters, where fractures may have given magma a route toward the surface. The surrounding deposits are interpreted as pyroclastic material, fragments thrown outward during explosive eruptions. Their broad, diffuse edges suggest that particles fell across the ground, rather than moving only as liquid lava. This is a different volcanic voice from the Great Plains. The plains record lava escaping and flowing across the surface. The pyroclastic deposits record gas expanding, magma fragmenting, and material being lofted above the ground. One process covers old terrain beneath sheets of rock. The other leaves a vent surrounded by a scattered mantle of particles. Some volcanic sites appear to have erupted more than once. Within certain pits, smaller depressions cut into larger ones. Deposits overlap. Crater counts and geological relationships suggest that explosive volcanism continued long after the earliest period of global lava flooding had declined. Mercury's interior was losing heat, but pockets of molten volatile material could still find routes upward. The timing is important. A small planet cools more quickly than a large one because it has more surface area compared with its volume. Mercury should have lost much of its internal heat early. The persistence of later eruptions shows that cooling did not shut down every source of magma at the same moment. Heat can remain concentrated. Radioactive elements release energy over long intervals. Differences in composition change the temperature at which rock begins to melt. Large impacts can fracture the crust and alter pressure below it. The deep mantle may cool unevenly, allowing some regions to remain capable of producing melt after others have become inactive. The sun also affects the appearance of volcanic deposits after they form. There is almost no atmosphere to protect loose material. Micrometeorites continually strike the surface. Charged particles arrive from the solar wind. Daytime heating and nighttime cooling place repeated stress on exposed rock. Over time, a bright deposit becomes altered, mixed, and partly hidden beneath later debris. What Messenger mapped was therefore not the fresh result of an eruption. It was the remaining trace after a long exposure to space. You can imagine the scene without making it violent. A fracture opens in the floor of an old crater. Magma rises through rock that has already survived countless impacts. Gas begins to separate as the pressure falls. Fragments leave the vent and travel across the low gravity of Mercury before returning to the ground. There is no air to carry the sound. The particles follow clean arcs above the surface. Larger pieces land near the opening. Finer material reaches farther outward. The deposit forms around the pit, exposed immediately to sunlight and the surrounding vacuum. Then the eruption ends. The fragments cool. The fracture becomes inactive. The sun crosses the sky through Mercury's long day, and the new deposit begins its own slow alteration. Elsewhere, lava moves in another way. A low curtain of molten rock feeds a broad flow. The leading edge advances over older ground, enters shallow craters, and surrounds ridges that remain standing like islands. The surface darkens as it cools, while heat continues to move beneath the crust. No observer was present for any of this. The events are reconstructed from shape, color, composition, and sequence. A buried crater shows that lava came later. A crater placed on top of the lava shows that impact followed. A vent without a rim points away from collision. A diffuse deposit around it suggests material scattered from within. The landscape becomes a set of physical relationships. There is also a limit to what the surviving record can reveal. Many vents may be buried. Thin flows may no longer be distinguishable. The oldest volcanic surfaces have been so heavily cratered that they blend with impact terrain. Some smooth patches may include both lava and impact melt layered together. Scientists work within that uncertainty rather than removing it. They compare surface forms with laboratory experiments, with volcanic plains on the Moon and Mars, and with the behavior of molten rock under low gravity and near vacuum conditions. They use spectral measurements to distinguish compositional units. They count craters to estimate relative ages. They examine where tectonic fractures cross volcanic deposits and where lava covers those fractures in return. Through those comparisons, Mercury emerges as a planet that remained active for a substantial part of its history. It was never only a cratered remnant left unchanged after formation. Its interior continued to reach the surface. Lava resurfaced broad regions. Explosive vents opened in damaged ground. Volcanic layers recorded changes in heat, chemistry, and pressure across immense intervals. The planet beside the Sun was not shaped by fire in one brief beginning. For a long time, the fire kept finding a way out. The volcanic plains did not remain level forever. As Mercury lost heat, its interior began to occupy less space. Metal and rock cooled. Portions of the core solidified. The mantle adjusted above them. The outer shell, already hardened into crust, could not shrink smoothly with everything beneath it. It had to break. Across Mercury, long cliffs rise where one block of crust has been pushed over another. These landforms are called lobate scarps because their fronts often curve in broad, rounded segments. Some cross crater floors, some cut through crater rims. Others continue for hundreds of miles across plains that were already old when the fault began to move. They are the surface expression of a planet becoming smaller. The amount of contraction is modest compared with Mercury's full diameter. Estimates based on the scarps and other compressional features suggest that the planet's radius has decreased by several kilometers since much of its crust became solid. Against a world nearly 5,000 kilometers wide, that change seems slight. For the crust, it was enough. Imagine a skin that has already cooled into a rigid shell. While the material beneath it continues to draw inward, the shell cannot remain perfectly fitted. Stress builds until a fault forms, and one section is forced above another. The ground shortens horizontally, while the scarp rises vertically. This process did not happen in a single moment. It unfolded across a large part of Mercury's geological history. Some scarps are old and softened by later impacts. Their edges have been struck, buried, and worn down by billions of years of exposure. Others are sharper. A few small scarps cut through relatively young terrain, suggesting that contraction continued long after the largest lava plains had formed. Mercury may not be finished cooling even now. No instrument has yet placed a seismometer on its surface, so there is no direct record of Mercurian quakes. But if faults still adjust as the interior loses heat, the planet could remain tectonically active on a limited scale. The motion would not require moving plates. It would come from the whole world continuing to tighten around a cooling center. On Earth, tectonic activity is organized largely by mobile plates. New crust forms at some boundaries, old crust descends at others, and continents move over the mantle. Mercury has no comparable global system. Its crust behaves more like a single outer shell, broken by impacts and faults, but not divided into plates that travel across the planet. That difference gives its tectonics a distinct pattern. Most of Mercury's large tectonic features show compression. The ground has been shortened, folded, or thrust upward. Lobate scarps mark the clearest examples. Wrinkle ridges cross volcanic plains where the upper layers were compressed into low, sinuous rises. Broad arches and ridge belts reveal stresses spread across wider regions. The direction of those features is not random, but neither does it follow one simple global grid. Local geology matters. A thick lava plain responds differently from fractured highlands. The rim of a large basin redirects stress. Buried structures beneath the surface can influence where faults begin. An impact may weaken one region while leaving another more resistant. The result is a planet-wide contraction expressed through local landscapes. One of the best-known scarps is Discovery Roups, first seen during the Mariner 10 encounters. It crosses the floor of an old crater and continues beyond it, showing that the fault formed after the crater. The cliff rises hundreds of meters in places, a long step in the crust created when one side was pushed over the other. The name may suggest a single wall, but a scarp is not usually a clean vertical face. its slope can spread across a broad zone. Fallen debris gathers below steeper sections. Later impacts cut into it. Sunlight exaggerates the relief when it arrives at a low angle, turning a gradual rise into a dark boundary across the ground. From orbit, shadows help reveal what color alone may hide. Mariner 10 photographed only part of Mercury, yet the scarps visible in those images were enough to show that the planet had contracted. Scientists could compare the faults with similar features on the Moon and estimate how much shortening they represented. The early estimates were limited because half the surface remained unseen. Messinger later mapped nearly the entire planet and found many more scarps, including long systems extending through regions Mariner 10 had never observed. With a more complete inventory, the estimated contraction increased. Mercury had not merely wrinkled in a few isolated places. Compression had reached around the globe. This changed the picture of its interior. A shrinking planet is a cooling planet, but the rate and amount of contraction depend on what the interior is made of, how heat moves through it, and when different layers solidify. Every mapped fault, therefore, becomes a clue to the thermal history below. If the core had cooled rapidly and become mostly solid early, much of the contraction should also have occurred early. If a large liquid portion remained for longer, the timing would be different. The chemistry of the core, including lighter elements mixed with iron, changes its melting behavior and the way it releases heat. The scarps cannot answer these questions alone. They work together with measurements of gravity, rotation, topography, and the magnetic field. The surface shows the accumulated strain. The orbiting spacecraft measures how mass is distributed. The planet's slight rotational variations reveal whether the mantle is fully locked to the core or able to move above a liquid layer. From these separate signals, a layered interior emerges. The crust sits above a thin mantle. Beneath it lies a core that occupies most of the planet, with liquid metal surrounding a solid inner region. The exact boundaries remain subjects of study, but the broad structure explains how Mercury can be both heavily cooled and still magnetically active. Contraction also changed the volcanic plains after they formed. A lava sheet may cool into a broad surface with few visible obstacles. Later, compression pushes portions together. Wrinkle ridges rise. Fault scarps cut across the plain. A surface created by material flowing outward is gradually reshaped by the planet drawing inward. In Caloris, the pattern becomes more complicated. The basin floor contains both compressional ridges and extensional troughs. Some regions were squeezed, while others were pulled apart. The impact had removed and fractured crust. Lava later filled the basin. As the floor adjusted, rose, cooled, and responded to stresses from the surrounding planet, different parts experienced different kinds of deformation. The radiating troughs near the basin's center belong to this more local history. They show that Mercury's global contraction was not the only force acting on the crust. Basin uplift, cooling lava, changes in pressure below the surface, and the geometry of the impact structure could produce extension even while the planet as a whole was shrinking. A world can contract globally and still stretch locally. This is one of the useful lessons held in Mercury's surface. Planetary geology rarely follows a single rule at every scale. The broad direction may be inward, while a basin floor pulls apart. The interior may be cooling, while pockets of magma remain. The crust may be old, while a small fault moves much later. Different clocks are running within the same planet. There is a familiar example in the cooling of ordinary materials. A metal pan removed from heat may contract as its temperature falls, yet different parts cool at different rates. Stresses appear where one region changes before another. The pan may bend slightly or make a brief sound as it adjusts. Mercury is not a pan, and its interior is far more complex, but the basic connection between cooling contraction and stress remains. On a planetary scale, the adjustment takes place over billions of years. A fault may move in separate episodes rather than sliding continuously. Long intervals of apparent stillness can pass between them. Each movement adds a little more height to the scarp and a little more shortening to the crust. Impacts continue throughout this process. A new crater may form across an existing fault. Later motion may cut the crater floor or offset its rim. By studying which feature crosses which, geologists can place contraction events within the relative history of the landscape. Some small scarps appear crisp enough to be much younger than the oldest plains. Their presence has led researchers to consider whether Mercury's contraction continued into the geologically recent past. The evidence does not provide a schedule of present-day movement, but it weakens the older idea that the planet became completely inactive billions of years ago. Even a small world can keep changing after its great eruptions have ended. The changes become harder to notice because they no longer cover continents with lava or excavate basins 1,500 kilometers wide. They occur along faults. They shift slopes. They open fresh surfaces to sunlight and space weathering. At the base of a scarp, loose material may slide downhill. A small impact can shake the surrounding ground. Temperature changes between day and night can weaken exposed rock. The cliff created by deep planetary cooling is then revised by processes acting only at the surface. Scale folds into scale. The core loses heat. The globe contracts. A fault moves. A cliff forms. Stones tumble down its face. From high above, the cliff becomes a thin line across a cratered plain. From the ground, it would be a horizon of rising rock, stretching beyond sight beneath a black sky. The sun would move with unfamiliar patience overhead. Shadows would remain long for days at a time. The shape of the scarp would become clearer, then fade into the glare as the angle of light changed. Nothing in that view would reveal the core directly, yet the cliff would exist because of events thousands of kilometers below it. This is how Mercury's surface connects with its interior, not through an open window, but through strain. The planet cannot hide the fact that it has cooled. Its outer shell carries the record in every thrust fault and folded plane. The impacts wrote circles. The lava wrote broad fields. Cooling drew long lines across them both. Those lines are still there, holding the shape of a world that has spent billions of years becoming slightly smaller. Beneath the contracted crust, part of Mercury's metallic core is still moving. That motion gives the planet something no other small rocky world possesses in quite the same way: a global magnetic field generated from within. The field is weak. Near the surface, it is only a small fraction of the strength measured at Earth. But weakness is not absence. Mercury carries a magnetic envelope into space, and that envelope changes how the solar wind reaches the planet. This was one of the most important surprises of the Mariner 10 encounters. Before the spacecraft arrived in 1974, many scientists expected Mercury to be too small and too deeply cooled to maintain an active magnetic dynamo. A planet of its size should lose internal heat relatively quickly. Its core might have solidified long ago. Without circulating liquid metal, there would be no enduring mechanism to generate a planetary field. Mariner 10 found otherwise. As the spacecraft passed near Mercury, its instruments measured a magnetic structure that could not be explained by the solar wind alone. The planet possessed an internal field, roughly dipolar in broad form, with a north and south magnetic orientation. The discovery forced a reconsideration of Mercury's interior. A magnetic dynamo requires electrically conductive fluid in motion. Inside rocky planets, that fluid is usually liquid metal. Heat escaping from the core, chemical separation as material solidifies, and planetary rotation can all help drive currents through the liquid layer. Those electrical currents produce a magnetic field that extends beyond the solid surface. Earth's dynamo operates within a large liquid outer core surrounding a solid inner core. Mercury appears to have a similar basic arrangement, but compressed into a much smaller planet with very different proportions. Its metallic core fills most of the interior. A significant outer portion remains molten, perhaps aided by sulfur and other lighter elements mixed with the iron. These ingredients lower the temperature at which the metal freezes. Even after billions of years of cooling, enough liquid can remain to circulate. The motion inside Mercury is probably not identical to the motion inside Earth. The core may lose heat slowly through the thin mantle above it. Solidification may release lighter material that rises through the liquid metal, creating buoyancy. The unusual size of the solid inner core may influence the shape and strength of the flow. Scientists test these possibilities with models that must account for several factors at once. The field is global, it is weak, it changes over time, and its magnetic center is displaced northward from the planet's geographic center. That displacement is one of Mercury's most distinctive features. If the field were a simple bar magnet placed at the exact center of the planet, its magnetic equator would align in a more symmetrical way with the geographic equator. Measurements by Messenger showed that Mercury's magnetic equator lies north of the geographic one. The field can be described as though the main dipole were shifted several hundred kilometers toward the north. This creates an uneven magnetosphere. Above the northern hemisphere, magnetic shielding extends farther from the surface. In the south, the field lines crowd closer to the ground. Charged particles from the sun, therefore, do not interact with every region in the same way. The solar wind is a continuous flow of plasma leaving the sun. It carries electrons, protons, and embedded magnetic fields through the solar system. Near Mercury, this flow is denser and more intense than it is near Earth, because the planet orbits much closer to the source. When the solar wind reaches Mercury, it meets the planet's magnetic field. On the day side, the pressure compresses the magnetosphere into a narrow region above the surface. Under strong solar conditions, that boundary can be pushed even closer. On the night side, magnetic field lines are stretched away from the sun into a long tail. The shape resembles a small cavity cut into a much larger stream. Earth's magnetosphere extends far into space and surrounds the planet with a broad protective region. Mercury's is compact. The dayside boundary may stand only a short distance above the ground by planetary standards. The entire system responds rapidly to changes in the solar wind. This response is not smooth. Magnetic fields carried by the solar wind can connect with Mercury's field through a process called magnetic reconnection. When the orientation is favorable, field lines break and join in new arrangements. Energy and particles are transferred into the magnetosphere. Magnetic structures move across the planet and into the tail. Messenger observed repeated events in which solar wind material entered Mercury's magnetic environment with striking efficiency. The field does not seal the planet away. It guides, redirects, and sometimes concentrates the flow. Charged particles can travel along magnetic field lines toward the surface. When they arrive, they strike atoms in the uppermost soil. Some surface atoms are knocked free and enter the space immediately around the planet. Others may be released by sunlight, micrometeorite impacts, or thermal processes. The result is an exosphere. Mercury does not have an atmosphere in the familiar sense. There is no dense blanket of gas, no weather system, and no layer capable of distributing heat around the globe. Instead, individual atoms move on long paths above the surface. They may rise, fall back, escape into space, or become ionized and swept away. The exosphere includes sodium, potassium, calcium, magnesium, hydrogen, helium, and oxygen. Its composition and shape vary with local time, solar activity, surface temperature, and the changing conditions of Mercury's orbit. Sodium is especially visible from Earth because it can scatter sunlight at particular wavelength. Observations have revealed a long sodium tail extending away from the Sun, somewhat like the tail of a comet, though produced by a different and more complex set of processes. This tail does not mean Mercury is dissolving all at once. The surface is being altered atom by atom. Material is released, transported, returned, and lost. Some of the escaping atoms are replaced when impacts expose fresh minerals, or when particles from the solar wind become embedded in the ground. The boundary between planet and space is therefore active, even without air. At Earth, the atmosphere creates a gradual transition. Pressure decreases with altitude, but gas remains present far above the ground. On Mercury, the transition is abrupt. Solid rock lies directly beneath an environment dominated by sunlight, plasma, micrometeorites, and magnetic fields. The surface is not beneath the sky. It is part of the space environment. The magnetosphere changes as Mercury moves around its eccentric orbit. At its closest point to the Sun, the planet experiences stronger solar radiation and greater solar wind pressure than it does farther away. Its orbital speed also changes, and the geometry between the solar wind and Mercury's magnetic field continually shifts. Solar eruptions can intensify the interaction. When a coronal mass ejection or other disturbance reaches Mercury, the magnetosphere may be compressed. More energy can enter the system. Particle precipitation may increase. At times, the dayside magnetic boundary may be forced so near the surface that portions of the planet are exposed to a harsher flow. Yet Mercury's field persists through these encounters. Its presence is evidence that the interior has not become completely static. Deep below the cliffs and plains, liquid metal continues to circulate. The motion is hidden, but its influence reaches into space. This connection runs in both directions. The core shapes the magnetic field. The magnetic field organizes the solar wind. The solar wind alters the surface and exosphere. Surface atoms then enter the magnetosphere and help reveal how the interaction is unfolding. A measurement taken thousands of kilometers above Mercury can therefore carry information from several layers at once. It may reflect the state of the Sun, the geometry of the magnetic field, the composition of the crust, and the movement of material inside the core. Messenger spent more than 4 years in orbit, gathering these kinds of measurements. It crossed magnetic boundaries repeatedly, sampled charged particles, tracked exospheric atoms, and mapped the field over different regions and phases of the solar cycle. Each orbit added another narrow path through the system. Over time, those paths became a three-dimensional picture of a planet surrounded by a small, restless magnetic environment. There is a human thread in this discovery. For centuries, Mercury was known mainly as a point of light that remained close to the horizon. It was difficult to see and harder to study. Its closeness to the Sun kept it low in twilight, where the atmosphere blurred the view. Even telescopes revealed little more than a small disk. Then instruments began to travel into the inner solar system. Mariner 10 crossed the magnetic field during a brief flyby. Decades later, Messenger returned to remain in orbit. Each spacecraft carried the accumulated work of engineers, physicists, geologists, navigators, and observers who would never stand on Mercury, yet learned to recognize the planet through signals too faint for any unaided sense. A tiny change in a magnetometer became evidence of a liquid core. A stream of sodium atoms became evidence of surface loss. A shift in magnetic latitude became evidence that the dynamo below was not centered in the way scientists expected. This is how an unseen interior becomes knowable. Not by opening the planet, but by following the influence that escapes from it. Mercury's magnetic field is too weak to create an Earth-like refuge. It cannot hold a thick atmosphere or prevent the surface from meeting the solar wind, but it gives the planet a structure beyond the rock itself. The world extends outward through invisible lines. Those lines bend under pressure, reconnect, trail behind the planet, and carry particles toward the ground. They create a changing region in which the Sun and Mercury are joined. The planet shaped by fire is still being shaped by contact, not by lava rising from below now, but by energy arriving from above. And between those two histories, the moving metal inside Mercury continues to hold a small magnetic space against the Sun. The Sun does not move across Mercury's sky in the way it moves across ours. Mercury turns slowly, but it also races around the Sun. Those two motions lock together in a pattern called a 3-to-2 spin-orbit resonance. For every 2 trips Mercury makes around the Sun, it turns 3 times on its axis. The result is a day unlike any other among the planets. One full rotation takes about 59 Earth days. One orbit takes about 88. But a sunrise to sunrise cycle lasts 176 Earth days, twice the length of Mercury's year. To stand on the surface through one complete solar day would be to watch the Sun take nearly 6 Earth months to return to the same place in the sky. The motion would not always seem steady. Mercury follows an elliptical orbit, so its speed changes. Near its closest approach to the Sun, it moves faster because its rotation continues at a nearly uniform rate. There are places where the Sun would appear to slow, stop, and briefly move backward before resuming its path. At some longitudes, sunrise would come in stages. The edge of the Sun might lift above the horizon, pause, sink slightly, and then rise again. Elsewhere, the Sun could climb, reverse for a time near midday, and continue westward. This apparent wandering is not caused by the Sun itself. It comes from the changing relationship between Mercury's orbital speed and its rotation. The Sun would be larger than it appears from Earth. Near Mercury's closest point, its disk would look more than 3 times wider. Then in our sky, sunlight would pour across the surface with an intensity that changes across the orbit. That changing distance matters. Mercury moves from about 46 million kilometers from the Sun at perihelion to nearly 70 million kilometers at aphelion. The difference produces a large swing in solar heating. Some regions receive especially strong sunlight when Mercury is nearest the Sun, while other longitudes experience their hottest conditions at different points in the cycle. Because the rotation and orbit repeat in the same resonance, this heating pattern is not spread evenly around the planet. 2 broad regions repeatedly face the Sun near perihelion. Over very long periods, they receive more intense solar energy than regions 90 degrees away in longitude. The pattern leaves what scientists sometimes call hot poles. Not at the geographic poles, but along the equator. The surface temperature responds sharply because Mercury has no substantial atmosphere to carry heat. At local noon near the equator, the ground can rise above 400 degrees Celsius. Before dawn, it may fall below -150 degrees. These are surface temperatures. A few centimeters beneath the ground, the temperature changes less. Deeper still, the daily cycle fades, and the subsurface holds a more stable record of average conditions. The long night allows heat to escape directly into space. On Earth, oceans, clouds, winds, atmospheric gases store and redistribute energy. Mercury has no comparable system. Sunlit rock warms, shadowed rock cools. The boundary between them can be abrupt. Along the rim of a crater, one slope may receive the full force of the Sun, while the opposite wall remains unlit. Heat and severe cold can be separated by only a few kilometers. Nowhere is that contrast more important than near the poles. Mercury's axis is tilted by only a tiny amount. Unlike Earth, it does not lean far enough to create strong seasons. Near the North and South poles, the Sun always stays low above the horizon. High crater walls cast long shadows across their interiors. In some deep depressions, sunlight never reaches the floor. These permanently shadowed regions are among the coldest places in the inner solar system. Radar observations from Earth detected unusually bright reflections near Mercury's poles. The signals resembled water ice. At first, the idea seemed difficult to reconcile with a planet so close to the Sun, but the geometry made it possible. A crater floor that never receives direct sunlight can remain below the temperature at which exposed water ice rapidly escapes. The surrounding terrain may be intensely heated, yet the interior shadow stays cold because there is no atmosphere to transfer much energy into it. Messinger later provided several lines of evidence for water ice in these polar deposits. Its neutron spectrometer detected reduced numbers of certain neutrons near the North Pole, a signature consistent with hydrogen-rich material beneath the surface. Laser measurements showed that many radar-bright regions matched permanently shadowed terrain. Thermal models indicated that some of these places were cold enough for ice to remain stable for very long periods. In the coldest locations, ice may lie exposed at the surface. In somewhat warmer shadowed areas, it appears to be covered by a dark insulating layer, perhaps a mixture of carbon-rich material delivered by asteroids and comets. That layer can reduce the rate at which the ice is lost. The presence of water does not mean Mercury once had rivers or seas. The ice is stored in small, scattered cold traps. Much of it was probably delivered by impacts over long spans of time. Comets, water-bearing asteroids, and perhaps chemical reactions involving the solar wind could all contribute. Most incoming water would not survive. An impact releases vapor and fragments across the surface. Molecules may bounce from one location to another, heated by sunlight, broken apart, or lost to space. A small fraction can eventually reach a polar shadow. Once there, it may settle into a place cold enough to remain. The process acts like a slow planetary sorting system. Material arrives across the globe. Sunlight removes much of it. Orbital motion and surface interactions move some of what remains. The deepest polar shadows become final resting places for molecules that happen to reach them. Over immense spans, even an inefficient process can build deposits detectable from Earth and orbit. There is something striking in the arrangement. At Mercury's equator, the Sun can heat the ground beyond the melting point of lead. Near the poles, within craters that have never seen daylight, water ice can persist. The planet does not average these conditions together. It keeps them side by side. This helps explain why a single temperature cannot describe Mercury. A world without weather can still have a complex climate of illumination. Latitude matters, longitude matters, slope matters, crater depth matters. The changing distance from the Sun matters. Even the shape of the horizon matters. On a flat plain near the equator, the Sun may dominate the sky for weeks. On the floor of a polar crater, the horizon may block it forever. The surface records these differences in ways that spacecraft can measure. Thermal instruments track how quickly regions warm and cool. Images taken at low sun angles reveal shadows and relief. Spectrometers measure composition. Radar reaches into darkness without requiring visible light. Each technique sees a different Mercury. Visible cameras show grey plains and crater walls. Neutron measurements reveal hydrogen. Laser altimetry defines the geometry of cold traps. Thermal models turn that geometry into estimates of long-term temperature. Together, they reveal a planet whose most valuable reservoirs may be hidden where no sunlight falls. The polar deposits also preserve a history of delivery. If their composition can be measured in greater detail, they may hold information about the kinds of objects that struck Mercury, the sources of water in the inner solar system, and the survival of volatile compounds close to the Sun. The ice is therefore not only a curiosity, It is a record. Some of that record may include organic rich material mixed into the dark layer above the ice. The word organic refers to carbon-bearing chemistry, not to evidence of life. Such compounds are common in primitive asteroids and comets. Their preservation in permanent shadow could offer a sample of material delivered across the inner solar system. Future measurements may help distinguish how much came from comets, how much from asteroids, and how much was produced or altered at Mercury itself. For now, the broad picture is clear enough. Mercury's orbit and rotation create a slow solar day. Its lack of atmosphere allows extreme temperature differences. Its nearly upright axis keeps some polar craters in permanent shadow. Within those shadows, water ice has survived beside the nearest planet to the Sun. The discovery changes the emotional scale of the landscape. Mercury is not only a place of heat, it is also a place where sunlight can fail to arrive. At the edge of a polar crater, the horizon would glow while the floor below remained black. The sun might trace a low circle just beyond the rim, never climbing high enough to touch the deepest ground. Above, charged particles would continue to move through the magnetosphere. Beyond the shadow, the plains would warm and cool through the long day. Beneath a thin, dark covering, ice would remain where geometry had protected it. The same planet can hold fire-lit rock and frozen water because there is almost nothing between the surface and space to soften the difference. Mercury keeps every contrast in place. For most of human history, Mercury never became more than a bright point near the edge of daylight. It stayed close to the sun in our sky, appearing briefly before sunrise or after sunset. The planet could be tracked, its position recorded, and its motion compared with the background stars, but its surface remained beyond reach. Even through telescopes, Mercury was difficult. The same atmosphere that makes sunsets possible also blurs objects seen near the horizon. Warm air rises, cooler air settles, and light bends through layers of changing density. A small planetary disk viewed through that moving air shimmers and loses detail. Mercury's apparent size also changes as it moves around the sun, but even at favorable times it remains small. Early observers sometimes believed they could see permanent markings and used them to estimate how quickly the planet rotated. For many years, the accepted answer was that Mercury turned once during every orbit, always keeping the same side toward the sun. It seemed reasonable. The moon keeps one face toward Earth because its rotation period matches its orbital period. Tidal forces can slow the rotation of a nearby body until such a lock develops. Mercury, orbiting close to the sun, appeared likely to have followed the same path. If that picture had been correct, one hemisphere would have faced constant daylight while the other remained in permanent night. The real pattern was found in the 1960s through radar. Scientists transmitted radio waves toward Mercury and listened for the returning signal. The reflected waves carried small frequency shifts produced by the planet's rotation. Different parts of the surface were moving slightly toward or away from Earth, leaving a measurable signature. The results showed that Mercury rotated once in about 59 Earth days. That value did not match its 88-day orbit. Instead, it revealed the 3-to-2 resonance we now know, 3 rotations during every 2 trips around the Sun. A planet, once divided into an imagined day, side and night side, became a world where every region eventually passes through sunlight and shadow. Radar offered information that visible light could not. It measured rotation. It mapped roughness. Later, it detected the reflective polar deposits that would eventually be identified as water ice. From Earth, radio waves could enter regions where sunlight never reached, but radar could not answer every question. To see the craters, plains, and scarps clearly, a spacecraft had to travel there. Reaching Mercury is more difficult than its closeness might suggest. The planet lies much nearer to Earth than the outer planets do during favorable alignments. Yet a spacecraft leaving Earth already shares Earth's rapid motion around the Sun. To move inward, it must lose a large amount of orbital energy. A direct fall toward the Sun would cause the spacecraft to speed up. It might cross Mercury's orbit far too quickly to remain nearby. Entering orbit requires the vehicle to reduce its speed relative to the planet, and carrying enough fuel for that change would make the mission heavy and expensive. The solution is to use gravity. A spacecraft can pass near a planet and exchange a small amount of orbital energy through the encounter. The planet's gravity bends the spacecraft's path. From the spacecraft's perspective, the flyby can alter speed and direction without requiring a long engine burn. This technique made the first Mercury mission possible. Mariner 10 left Earth in 1973 and passed Venus before continuing inward. The Venus flyby changed its course so that it could meet Mercury. It became the first spacecraft to use one planet's gravity to reach another. Mariner 10 flew past Mercury 3 times in 1974 and 1975. It did not enter orbit. Each encounter lasted only a short time, but the spacecraft returned the first close images of the planet. The photographs revealed a heavily cratered surface. They showed the edge of Caloris, long scarps crossing old terrain, and broad plains between craters. Instruments detected the magnetic field and sampled the planet's thin exosphere. Yet the timing of the flybys created a limitation. Mercury's rotation and Mariner 10's orbital path brought the spacecraft back to nearly the same illuminated hemisphere during each encounter. Much of the planet remained unseen. The first close portrait was therefore incomplete. For more than 3 decades, maps of Mercury contained large blank regions. Scientists knew that the photographed hemisphere held ancient impacts and global contraction, but they could not assume the unseen half looked the same. The next mission was designed to stay. Messenger launched in 2004. Its name referred to Mercury's surface, space environment, geochemistry, and ranging, a list that described the many parts of the planet the mission was built to study. Its journey took years. The spacecraft flew past Earth once, Venus twice, and Mercury 3 times. Each encounter adjusted the orbit around the Sun, gradually bringing the vehicle closer to Mercury's speed and path. In 2011, Messenger finally entered orbit. For the first time, a spacecraft could observe Mercury through changing seasons of illumination, repeatedly crossing different latitudes and longitudes. The blank regions disappeared from the maps. The planet became global. Messenger measured topography with a laser. It mapped elemental abundances with spectrometers. It tracked variations in gravity and rotation. It recorded the magnetic field, the exosphere, and the changing response to the solar wind. Its images revealed widespread volcanic plains and hundreds of explosive volcanic sites. It found hollows, unlike landforms known elsewhere. It showed that the magnetic field is shifted northward. It confirmed hydrogen-rich deposits near the poles and strengthened the evidence for water ice inside permanent shadow. The mission also showed that Mercury had not followed the simple history once assigned to it. The surface chemistry did not fit a world stripped clean by extreme heat. The plains showed extensive volcanism. The small scarps suggested contraction continued later than expected. The interior remained partly molten. Each discovery removed another part of the old picture of Mercury as a finished, inactive stone. Messenger's orbit gradually changed under the influence of solar gravity and the uneven gravitational pull of Mercury. Engineers used the remaining fuel to adjust its path and extend the mission. Eventually, the propellant was exhausted. In April of 2015, the spacecraft struck Mercury's surface. The impact ended the mission and added one small crater to a world already marked by billions of years of collisions. The data remained: years of measurements, continued to be studied after the spacecraft was gone. New results could be drawn by combining image sets, comparing instruments, and improving models of the interior and surface. A mission does not end at the same moment as its signal. The observations can continue changing what is known long after the vehicle itself has become part of the landscape. The next major exploration effort is Bepi-Colombo, a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency. It was launched in 2018 and was designed around two orbiters that will study Mercury from complementary paths. One orbiter focuses on the planet's surface, composition, gravity, and interior. The other focuses on the magnetic field, charged particles, and the surrounding space environment. Together, their measurements are intended to connect the deep interior with the crust, the exosphere, the magnetosphere, and the solar wind. This connection is where many of Mercury's remaining questions meet. Why is the core so large? How did the planet retain volatile elements? When did its major volcanic activity end? Are some faults still capable of movement? How is the unusual magnetic field produced? What is the full history of the polar ice? No single instrument can answer all of these. A camera can identify landforms, but not directly measure the deep core. A magnetometer can trace invisible fields, but cannot determine the age of a lava plain. A spectrometer can identify elements while leaving the geological sequence uncertain. Understanding comes from overlap. The shape of a scarp is compared with the age of the plane it crosses. Magnetic measurements are combined with models of core motion. Polar temperatures are compared with radar reflections and hydrogen detections. Gravity is considered beside topography and rotation. The planet is reconstructed from different kinds of evidence, each one incomplete on its own. This is also how Mercury has slowly entered human knowledge, first as a wandering light, then as a small telescopic disk, then as a radar echo carrying the rhythm of rotation lengths, then as a partial world photographed during 3 brief encounters, and finally as a mapped planet layered with impact basins, lava plains, shrinking crust, magnetic motion, and ice held inside shadow. Every method widened the view without finishing it. Mercury still keeps much of its beginning hidden. Its oldest crust has been broken and covered. Its mantle cannot be seen directly. Its core be understood only through the signals that reach the surface and space. But the distance between mystery and knowledge has narrowed. A point once lost in twilight has become a world whose cliffs can be measured, whose elements can be mapped, and whose long day can be followed from orbit. The instruments arrive for a while. The planet remains, carrying the questions into the next pass above its surface. Mercury is often described through extremes. It is the closest planet to the Sun. It has the shortest year. Its surface moves between intense heat and deep cold. Its core is unusually large. Its magnetic field is unexpectedly persistent. Its polar shadows preserve ice beside a world flooded with sunlight. But extremes alone do not explain the planet. What makes Mercury valuable is not that it is the most dramatic version of a rocky world. It is that so many parts of planetary history remain visible there at once. The planet still carries the chemistry of its formation, though that chemistry has not yet revealed exactly how so much metal came to dominate the interior. Its oldest terrain retains the marks of early bombardment, though later impacts have broken and mixed the record. Its volcanic plains preserve the release of internal heat. Its scarps measure the gradual contraction that followed. Its magnetic field reaches outward from liquid metal, still moving beneath a crust shaped billions of years ago. Every layer points toward another. The oversized core raises questions about the beginning. The sulfur-rich surface limits which origin stories can work. The volcanic plains show that the interior remained active after the earliest collisions. The faults reveal continued cooling. The magnetic field shows that cooling did not freeze the core completely. The planet cannot be reduced to a single event. Perhaps Mercury began with unusual material near the young sun. Perhaps collisions later changed its proportions. Perhaps solar heating removed part of its early surface. Each explanation may contain part of the answer, but the present world requires those ideas to fit the same evidence. That is, the patient difficulty of planetary science. A theory cannot explain only the feature that inspired it. It must also survive everything else the planet reveals. A giant impact may account for lost rock, but it must also account for retained volatile elements. An intensely heated beginning may explain some chemical sorting, but not a surface richer in sulfur than expected. A metal-rich formation region may help explain the core, but it must fit the broader history of the inner solar system. Mercury keeps all of these questions open because its oldest evidence is incomplete. There is no untouched piece of the planet's first crust waiting in plain view. The original surface has been cratered, melted, buried, fractured, and weathered by space. What remains is not a preserved beginning, but a set of consequences. Scientists work backward from those consequences. They measure density and infer internal proportions. They track small changes in rotation and detect a liquid layer below. They map elemental abundances and rule out overly simple formation models. They study faults and estimate how much the globe has contracted. They follow exospheric atoms and learn how the surface interacts with sunlight and the solar wind. This form of understanding grows through limits. No spacecraft can watch Mercury form. No instrument can descend through its mantle and enter the core. The past has to be reconstructed from what matter still remembers. Rock remembers through composition. Crust remembers through deformation. Basins remember impact. Ice remembers shadow. The magnetic field remembers motion far below the surface. These memories are physical rather than conscious. They remain because one event changes the conditions for the next. A collision opens a basin. Lava later fills it. Cooling compresses the lava into ridges. Another impact cuts through those ridges. Sunlight alters the exposed fragments. The history does not sit in separate chapters on the ground. It is layered into the same place. A single crater floor may contain material excavated from depth, lava that arrived after the impact, fractures formed during later contraction, and bright hollows created through a process that may have continued much more recently. From orbit, all of those times can appear together. This is one reason Mercury rewards careful observation. Its grey color can make the surface look uniform, but shape, chemistry, texture, elevation, and reflectivity reveal differences that ordinary vision would miss. A plane that seems empty may be the cooled surface of repeated eruptions. A low ridge may mark compression across a buried lava sheet. A dark polar floor may hold water delivered from distant regions of the solar system. A faint magnetic measurement may carry information from the deepest part of the planet. Nothing about Mercury is isolated. Its orbit controls the motion of the sun across the sky. That motion creates patterns of heating. The slight tilt of the axis protects the polar shadows. The lack of an atmosphere preserves strong temperature differences. The magnetic field redirects charged particles. Those particles help release atoms from the surface. The surface composition reflects materials assembled near the early sun. The planet is a network of connected processes. Some act over minutes. Solar particles strike the ground and free atoms into the exosphere. Some act over a Mercurian day. Rock heats beneath the sun and cools during the long night. Some act over millions of years. Impacts slowly cover the surface with new craters. Some act across billions. The interior loses heat, the core evolves, and the crust shortens around it. Mercury moves through all of these times at once. At this moment, the planet continues around the sun. at greater speed than any other planet. Its surface passes through light and shadow. Sodium atoms rise above the ground. The magnetosphere changes under the pressure of the solar wind. Ice remains within craters where direct sunlight never arrives. Far below, the metallic interior continues its hidden adjustment. The great volcanic plains are no longer spreading. The largest basins are no longer forming with the frequency of the early solar system. Yet, the planet is not separated from its past. Its present shape was produced by that past, and every current process acts upon what earlier processes left behind. Even the sun has changed. The young star that shone over Mercury's formation was more magnetically active and surrounded by a disk of remaining material. Over time, the disk cleared. The planet settled into more stable paths. The rate of large impacts declined. The sun brightened gradually as hydrogen was transformed in its core. Mercury endured those changes from the innermost planetary orbit. It did not remain untouched, but it remained. There is a kind of clarity in that survival. Not the clarity of a simple world, but the clarity of material continuing to obey physical laws through every stage of change. Rock melts when conditions allow. Metal sinks when gravity separates it from lighter material. Crust breaks when stress grows too large. Ice survives where energy cannot easily reach it. The planet does not need to preserve every detail for the larger pattern to remain. Heat moved outward. The interior cooled. The surface hardened. Impacts interrupted it. Lava covered it. Faults shortened it. Sunlight continued to work upon it. Through all of this, Mercury became the world now seen from orbit. Dense, cratered, chemically surprising, magnetically alive, and still difficult to place within a single origin story. Perhaps future measurements will narrow that story. They may define the thickness of the crust more precisely, improve models of the core, identify the chemistry of the polar deposits, and reveal more about the timing of volcanism and faulting. Some questions may become clearer. Others may divide into smaller questions. That is often how exploration proceeds. A distant point becomes a disk. The disk becomes a landscape. The landscape becomes many systems interacting across time. Each increase in detail removes one kind of uncertainty and reveals another beneath it. Mercury began in human awareness as a wandering light near the horizon. It became a planet of mathematical motion, then a world of craters, then a volcanic world, then a contracting world with a living magnetic interior and water hidden in darkness. None of those earlier views was useless. Each was incomplete. The planet had not changed between them. Only the depth of attention had changed. And now, as Mercury continues along its narrow path near the Sun, its surface carries the accumulated result of fire, impact, cooling, and time. Beyond the twilight, Mercury keeps turning through the Sun's light,